Good morning and welcome to Computer Science 21. We're going to finish up our talk today on Chapter 8, and the big thing we're going to talk about here today are these things called interrupts. And already I'm having technical difficulties here, so please bear with me as I get all of my ducks in a row. So we're talking, this is terribly annoying. I'm going to try this one more time. I don't want to do that. I think I know what I need to do here. I need to come over here and do that. And now it should work. So we're talking about interrupts. And I don't know why I'm having trouble writing. If I were good at these videos, I would stop this now and start all over again. But I'm not so good at these things. interrupts. This is very important. We have some important stuff to talk about in here. So I'll say important. But I'm also going to say that what I'm going to talk about, what I'm about to talk about is not in the book. So you need to listen up carefully, okay? I want you to imagine the following situation. We've been drawing memory. So here's memory over here. And for a second now, when we've been talking about the LC3, we've sort of been assuming that we have this computer and it's only a single user computer. And that's very 1960s, but certainly not 2020s. Even when I'm sitting here with my personal computer, my desktop computer, there are several different processes that are running at once. For example, right now, I am running a video capture program. I'm running this program over here to draw. There's stuff going on in the background that I'm doing. So what's going on here is if we were to look inside of my program memory here, over here might be a program. And over here might be another program. And there could be several different programs running at once. Okay, we could be running on a network. These could actually be programs that different people are running. But I want you to consider the following situation. Let's suppose that we are actually on the internet, and there are a bunch of us on the internet, and we've just gone to Travelocity, and we want to make a reservation on a particular airplane. We all want to fly down to Florida, where it's nice and warm. It's still kind of cool where I'm making this video. So there's a particular flight, and what happens is right over here at this variable location, right over here, I'm going to just mark it with a star. This is how many people are currently on the plane. So I'm going to say current number of people on plane. And maybe the current number of people that have reservations on this plane, maybe there are 72 of them. Okay, and over here, person A, I don't know why I'm having so much trouble with my tablet today, but I seem to be. And here's person B. And they are both sitting in front of their terminals. And they're looking at this particular flight. So they're both running a program, and they want to know how many people are on the flight, and this thing comes up there, and it says 72. And this person over here is looking at it, and it says 72. And what happens is this person A wants 3 tickets. And let us suppose that B wants 4 tickets. Okay? So here's the point, here's the important point that I want to make about this. And let me go ahead and save that because I need some more space here now. So we can imagine over here, here's person A's program. So you can imagine that A is over here. And over here, again, you may remember, let's just call this num. And it's got 72 in it. And we can imagine in program A's program, we do something like the following. We load R0 with num. We said A wants 3 tickets, so we could say add to R0, 3. And then what happens is we say store R0 at num. Okay, and that's A's program. And we can imagine that B's program might look like the following. A technical difficulty here, we'll have B use different registers. So B might say load R1 with num. And then what we might do is we might say add R2, let's see, I'm sorry, that's a mistake. Let's add to R1, and 4. And now let's store R1 back at num. Okay? And the thing is we can imagine the following thing happens. We can imagine that first we execute this, and then what happens is 72, of course, would go to 75, and then we execute this. And what would happen is num would now go from 75 to 79. Likewise, on the other hand, we can imagine that we executed this first, and it would go from 72 to 76, and then we execute this, and it would go from 76 to 79. But the point is what we want. We want what's called serializability. Big word. Serializability. Okay? And what that means is we ultimately want to see what should end up in here is going to be the same as if I executed this and then executed this, or if I executed this and then executed this. Okay? I hope that's clear to everyone. Now, the reason why I'm introducing this is there's this whole notion inside of a computer of what's called an interrupt. And normally what goes on is I want you to realize that when you have multiple programs that are running inside of a computer, what happens is there's an alarm clock that goes off every once in a while. And that alarm clock is a kind of interrupt. And what happens when that alarm clock goes off is we're in the middle of executing one program, and at some point, and who knows where in that program, the alarm goes off, we stop executing this, and what happens is we go over and we start executing this. And while we're executing this, at some point, an alarm clock goes off, and we stop executing this, and who knows where we stop executing this, but then we'll go on to yet another program, and then on to another program. So what's going to happen over here is as if from the CPU's point of view, the CPU is actually doing something like this. It might be doing A's program, and it could be doing the load R0 num, and then what could happen is over here, we could still be doing A's program, and we're doing add R0 number 3. And now the alarm goes off. And the alarm goes off, and what we're going to do now is now we're going to come over here, and we're now going to start executing B. And we come over here, and we say B, and we start going load R1 num. And then B is going to do add R1 4, and then maybe B gets to execute the store, so B is now going to do store R1 num. And now the alarm goes off, and we go back to A. And I come back to A, and I do something like this. And A was just about to do this store, and I would do a store R0 num. Now I think you can see what the problem is here. What's happening over here, these, okay, what's going to happen is R0 is going to get a 72. Okay, and then what's going to happen is R0 is then going to become 75. Okay, but now what's going to happen over here is R1 is going to get a 72. And then we're going to add 4 to it. It's going to become a 76. And now what happens over here is num gets 76 written back to it. So num gets 76, and then what happens is I come over here, and now num is going to get 75. And that, of course, isn't the number that should be there. The number that should be there at this point now is 79. There's a key point here. First of all, we can see that when we do this, it's no longer serializable. And what happened here is that we had two different processes that were both accessing the same thing. And in fact, not only were they accessing it, but they were going to modify it. So the point here, this brings up a very, 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 very important concept in operating systems, and you'll learn about it, and it's what's called a critical section. And what a critical section means is it means that if there is a certain resource, and a resource could be memory, that is accessed by more than one process, okay, like we have in this situation over here, it is important that you let the whole thing go to completion. In other words, what I want to do is when I start to execute this code right over here, I don't want to allow an interrupt to come in. I don't want any alarms going off while I'm executing this right here. So the point is I don't want interrupts, and that's something that we're going to talk about right now. Interrupts are something that can be enabled and disabled. And when you're executing certain bunches of critical code, you want to actually disable the interrupts because you don't want this being interrupted in the middle and something else accessing the same resource. In this case, it would be the variable that's called num. Okay? So the idea here is that you have interrupts you can enable them or you can disable them. Okay, and you disable interrupts you disable to enter critical sections. Okay, important. Now, why do I bring that up? Well, again, we took a look at the keyboard. We also took a look at the display, and you may remember there was always a status bit. So we came over here, and we had a status register. Okay, and it was always this leftmost bit right over here. This was the status bit. And remember, we always went into these polling loops. And what the polling loops were is they kept cycling around as long as that was a 0. As long as there was a 0 there was really nothing to do because the device was busy. And then when it came back and it was 1, that's when we could either read a keystroke from the keyboard, or that's when we could display another character on the monitor. Now, the problem we said with polling is polling wastes time. What we want to do now is we want to change this from polling to interrupts. And what we're going to do is in this status register, there is going to be another bit over here. And this is going to be the interrupt enable bit. And the way that this works now is we take the output of these things and we feed it into an AND gate. And this over here is called the interrupt line. And we can see that the interrupt line only goes high when we've enabled interrupts and there is actually something to do. In other words, when the status bit is a 1, which means that there's either a keystroke to read or there is a character to display on the keyboard. Now, the question is where does this interrupt line go? Very good question. Let's take a look at a CPU. Okay, now we've been used to looking at a CPU as this thing from the inside. I want to look at it from the outside. When you look at it from the outside, again, and now I'm talking about an actual computer chip. So here's a computer chip right here. I know that's a very bad drawing. And again, there are lots of lines going into the computer chip. And in fact, if you were to look inside the computer that you're all using right now, there are quite a few of these lines. I think something on the order of about 250 of them. Okay? Several of these lines, and I don't know which ones they are, but I'll just make a drawing look good. I will circle these, and these are the interrupt lines. And again, you could have one interrupt line for the keyboard. You could have an interrupt line for the mouse. I'm using a tablet right now. So they could be a whole bunch of these things. You can have a whole bunch of different devices that have their own status registers like this. And what happens is they go to each one of these, each one has their own line right there. Okay? Let me save this. Now, you may recall way early in the semester we were talking about the execution of a computer program. And we said that basically what we do is we let the, let's see, I want to make sure I get this right. We let the instruction register get memory of the PC. And then we said that the PC gets PC plus 1. And we said, then we execute the instruction register. And then we said we just go and we repeat this all over again. And that this was the basic execution of a working computer. Now, what we want to do is we actually want to change this diagram a little bit. And I know we've done this already, so this is not going to be new. We come over here and we say the instruction register gets memory of the PC. We said the PC gets PC plus 1. We execute the instruction register. And then we come down here and we ask a question. Was there an interrupt? I'm going to just come over here and I'm going to say interrupt. And what that means is, did any one of these lines over here get a signal? Okay. Now, if they didn't get a signal, then there's nothing new to do. And if the answer is no, then we just come over here and we continue the way that we did before. Okay. But if the answer is yes, we have a couple of things we need to do. The first thing we need to do is we need to save PC and flags. And we will discuss later in the class where we save them, but they have to be saved. Then what we need to do is we need to determine which line interrupted. Okay. We have to call the appropriate interrupt routine. Remember, what's going to happen here is each one of these different lines is going to have a different routine associated with it. Then what we're going to do, I'm running out of room here. I'd normally be drawing it down, but I'm going to come over here. Once I'm done with that, I need to restore the PC and flags that I saved over here. And then from there, I can go back around here. Kind of a messy thing. Okay. So then the question is, how do I determine which one of these interrupts gets called? And the answer to that is coming back to these drawings right over here. And now I'm going to put this back in LC3 jargon. What happens when these lines over here each have numbers on them? Okay, so that when an interrupt occurs, the CPU can start looking at these lines and go, oh, this was line number 1 that did it, or it was line number 7, or it was line number 23, or whatever the numbers are here. Here they might go sequentially. It could be 1, 2, 3, 4, 5, something like that. So in the LC3, what it's going to do it determines which line caused interrupt it adds hex 10 actually 0100 to the line number, and invokes the appropriate interrupt routine. Well, first of all, I want you to remember something here. When we talked about traps, on the LC3, we said all the way here from 0000 all the way up to hex 00FF. This was called the trap vector table. And remember what this did. This contained the address for where the code was for trap 0. The next one, this contained the address for where the code was for trap 1, all the way up to trap 00FF. Well, it turns out over here, from here all the way up to here, this is called the interrupt vector table. So what happens over here, for example, suppose that it was line number 3 on the pin over here, suppose it's line number 3, that caused the actual interrupt. So I'm going to add hex 100 to it, and I'm going to come over here to hex 0103, and this is going to contain the address right in here of the particular routine that I should execute for that interrupt. Okay? So you can see that interrupt vector table is very much like the trap vector table. These you call, okay, the program calls these. This is program control. This over here is computer control. Okay, in other words, these I call from within my program. These I have no control over. In other words, maybe my program, so I want you to appreciate what's going on here. I'm running my program, and now all of a sudden somebody walks over to the keyboard and just starts pounding the keys, okay? They start hitting the keys a lot, 30 keys a second. That's generating 30 interrupts. And what's happening is that is actually halting the currently executing program. It's going to the keyboard interrupt vector, which is someplace in here, where it's going out to the keyboard, it's reading the scan code, and it's going and it's saving that scan code in a buffer. I'm sure you've all had the experience of typing ahead on a program, and somehow or other when the program catches up with you, it knows what the keystrokes are that you hit. That's because when you were hitting the things early, it was still storing the keystrokes somewhere. So that's how interrupts work. And the other thing, the key point that I also want you to take away from here is that there are times, I'm trying to find, it's right over here, there are times that you actually want to disable the interrupts because there are times that you're executing critical code. So that's why over here in the status register, okay, there is the ability to actually disable interrupts. You don't want to do it. Now, there's just one more thing that I want to say over here. We said that when an interrupt occurs, and I'm looking for my other drawing here, right here. This is a very key point right over here, where it says determine which line interrupted. Okay? Because remember, what's going to happen is remember that any one of these lines over here could cause the interrupt. So I want you to think about something. So somewhere the designers of the computer have written code and it says, okay, I'm going to check. Did this line cause the interrupt? If the answer is no, go check this line. Did this line cause the interrupt? If the answer is no, go ahead and check this one. Did this line cause the interrupt? Now I want you to notice the way that I checked these. I checked this line first, this line second, this line third. Now suppose both of these lines interrupted here. Well, if you take a look at the way that we drew the flowchart, if both of these interrupted, I'm checking this one before I'm checking this one, which means that I would handle this interrupt before I would handle that one. And what that means is that I've imposed a priority on it. Okay? So what happens is you can, my cat, thank you. What happens is you can impose priorities on interrupts. Okay, and again, what that means is suppose these are 3 different interrupt lines, and suppose the CPU has figured out that there's an interrupt. And suppose we decide we'll check this one first, we'll check this one second, we'll check this one third, we'll check this one fourth. Okay, and like I said, whichever one we determine caused the interrupt, we're going to go ahead and surface that one first. So let's suppose that at one point both 1 and 3 generated an interrupt. Okay, now because I'm checking line 1 before line 3, I'm going to service interrupt 1 before I service interrupt 3. But then I want you to think about the following. Suppose that while interrupt 1 is being serviced, somebody comes along and generates, or something generates interrupt 2. So now what's going to happen is when 1 is all finished, I'm going to go ahead and I'm going to service interrupt 2. Now let's suppose that while we're servicing interrupt 2, interrupt 1 occurs. So when interrupt 2 is finished, now what's going to happen is I'm going to service interrupt 1. And you can see poor interrupt 3 is sitting here and it's never getting serviced. So depending upon the situation, that may be okay. The point that I'm trying to make here is that it's very important on how you impose your priorities on the interrupts. Okay? In other words, how you order up these lines is very, very important, because it could be the case that there may be interrupts with very low priority that we could never get to. That's very doubtful, but it is possible. So again, I want to reiterate that this is a slightly different presentation than your author presented in the book. I hope it's helpful, and we are finished.